Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Now for this video, we are from group 10 and section 1 need to present about the project presentation. The title is Basic Phase Angle Analysis in Power System Using Symmetrical Components. Let me introduce my group member first. Firstly, my name is Ajmal Danish bin Muhammad Zamri. The Metikas number is CE21027. Second, Muhammad Aziz bin Muhammad Noor. The Metika is DE2000554. And the third, Muhammad Ali Mustaqim bin Muhammad Shuhaimi. The Metikas number is CE210188. Fourth, Muhammad Nizam bin Zahari. The Metikas number is CE210005. And the lastly is Muhammad Shafiq bin Abdul Rahman. The Metikas number is CE210015. Next, the introduction for this project is, this project focus on analyzing phase angle in power system using symmetrical component to understand their impact on power system operations. Particularly, during fault condition, phase angle are crucial for ensuring network stability and reliability, as they indicate the time relationship between voltage or current waveform. Symmetrical components provide a mathematical framework for breaking down large three-phase system into independent and balanced components, making it easier to analyze system behavior under different operating conditions. Positive, negative and zero sequence component represent ideal balanced system, while negative sequence component cause overheating and potential damage to sensitive device. So the understanding phase angle during fault condition is crucial for recognizing and managing disruption, and symmetrical components offer a systematic approach to assessing fault effect and developing preventative measures. Next, we go to the objective for this project. So, objective for this project, we have three. For the firstly is learn the theory behind phase angle and symmetrical component in power system. And the second for this project, we need to conduct a basic analysis of phase angle using symmetrical component. And the lastly for objective for this project is understand the impact of phase angle variation on power system stability. Then, the problem statement for this project is a significant barrier is the fundamental theory governing phase angle and symmetrical component in power system. To address this intensive research is needed to clarify the principle determining phase angle behaviors and importance of symmetrical component in electrical networks. Improved analytical tools, simulation methodologies, and practical application are needed to enhance the understanding and study of phase angle. Through research, simulation, and analysis are also needed to assess the impact of phase angle fluctuation on system stability, parameter, voltage profile, transient response, and overall system resilience. So next, I will pass to Muhammad Aziz to present about the methodology.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Aziz bin Muhammad Noor. So today, I'm going to present the methodology part for power system protection assignment project. So as we can see that the software that our team used to analyze the basic phase angle analysis by using the symmetrical component, we use the MATLAB and Simulink MATLAB software with the Simulink 8 block diagram software. So by using MATLAB, we are able to convert the mathematical model to analyze inside electrical power system network. So in MATLAB, we can analyze any type of model that we want, such as mechanical model, electrical model, electromechanical model, and convert it into mathematical model block diagram, and we can analyze it back to the electrical power system network model. So the main parameter that we would like to analyze using MATLAB Simulink is the phase angle during pre-fault, before fault occurs, and critical clearing time from the fault time decline, and the active power from load. And next, for the symmetrical component use, we would like to analyze a two-area system network for a power system network simulation line. So based on a P-Condor power system stability and control textbook, so these are the transmission line that contain inside a P-Condor power system dynamic and control textbook. So the two-area system network consists from generator 1, generator 2, generator 3, and generator 4. Area 1, which consists of machine and turbine for machine 1 and machine 2, and area 2, which consists of machine 3 and machine 4, turbine and regulator. So both each rating of the bus 1, which is area 1, and bus 2, area 2, consists of 900 MVA of apparent power, demand power, and a 20 kilovolt of bus voltage on each bus. So based on the area 1 and area 2, on the output of MATLAB scope, area 1 and area 2 holds the yellow and blue color output on scope, while the area 2 holds green color and orange color output on the MATLAB scope. So these are the symmetrical components that we will use to analyze. So we continue on the current slide. Based on the previous slide is the sketch of the power system simulation network on the pre-Condor textbook, and these are the simulation on Simulink. So these are the same network that I show previous. So on the MATLAB Simulink, the output for each machine we will observe on the machine scope. As we can see, there are four types of output, which is the phase angle or rotor angle versus machine generator 4, electrical power for each machine, speed in radian per second of each machine, machine speed, and lastly is the voltage produced, output voltage produced for each machine. So for this project, we would like to analyze the output of scope number 1, which is the d theta versus m4, which is the phase angle, and we would like to apply fault by using the 3-phase fault, and we set the fault time duration, which is interval for each second to determine the clearing time, critical clearing time. So this critical clearing time determines how long does the system can withstand before fault occur. So for the d theta versus m4 angle, which is the rotor angle and phase angle of the machine, we need to declare the center of inertia. So the center of inertia is equivalent to the sum of phase angle for all 4 machine generators divided by the mass of inertia for all 4 generators. So after we declare all of that, and we can run the simulation to determine the phase angle and apply fault interval in time per second, so that we can analyze the critical time and maintain the active power load for each bus 1 and bus 2. Next is the flowchart part. For the methodology, we provide the flowchart of process in order to solve the problem to determine the phase angle analysis and fault time, critical clearing time required to stabilize the phase angle condition in power system stability. So first, on the flowchart we start, and we need to declare the center of inertia for phase angle for all 4 machine generator on area 1 and area 2. Like I mentioned before, the center of inertia formula is the sum of all 4 machine phase angle divided by the sum of all mass inertia for all 4 machine generator. And after we declare that on the Simulink block, we will have the total 4 types of angle on the output scope. And after we declare the center of inertia, we need to adjust the fault time on the 3-phase power system Simulink block. We adjust the fault time in seconds. And after that, the decision block shows that the critical clearing time is longer during fault duration. If it is shorter, it will go back. We need to adjust the fault time back. And if it is longer, the critical clearing time is longer. After we adjust the fault duration, we proceed to decrease the active power on up to 10%, increment for 10% for bus 1 and bus 2 on area 1 and area 2. And after that, if the phase angle rotation or rotor angle rotation achieve the stability state, we maintain the active power load for bus 1 and bus 2 on area 1 and area 2. But if the phase angle have not achieved the stability state, we need to decrease back the active power back up to 10% until the phase angle achieves stability state. And that is the process we use to solve the problem of phase angle analysis using symmetrical components. So these are the flowchart that show the procedure. So that's it from me. Thank you.
Assalamualaikum. My name is Muhammad Anis Mustaqim bin Muhammad Syaini, and my metric number is CE210188. Okay, I will present about the simulation process. So first, open the MATLAB software. Then this is our circuit. We have for area 1 is generation part, and area 2 is for the load part. Okay, next we need to do this COI, which is then connected to theta 1, theta 2, theta 3 and theta 4. After that, we just connect the fault here, 3-phase fault, to the 3-phase line, and we set it for 5 options, which is the first one is 1.5, 2.5 and 4.5, 8.5, and the last one is 9.5. Okay, for the first simulation, I will show you the 1.5 option. So just insert the value here for 1.5 and press apply. Okay, and then press run. So wait for like 5 seconds or 10 seconds, and we will pop the graph here. So from the graph you can see this is the d theta graph, power per unit, watt per unit, and VT per unit. So from the d theta we can see that this is the stable when the data is stable. Then when we do the fault time at 1.5, it is 1.5, and it will become unstable. So this is unstable. So to look it better, we look at the VTPU. So this is the fault time that we entered in the 3-phase fault, which is 1.5, and this is the critical clearing time before it become unstable, which is we got 2.076 at phase angle 1.144 e power of 2. So for the next value, just repeat the process but change the value here for 2.5. That's all from me. Thank you.
Assalamualaikum, my name is Muhammad Nizam bin Zahri. Today I will present about the result and analysis. For this graph, show when the fault time is set to 1.5 seconds, the critical time is 2.075. The crucial clearing time is the amount of time required to clear a problem in the power system such that it remains stable and operates normally. This graph showed that the graph became stable after 3.6 seconds and has an angle of 8.45 degree. Then I will pass to Shafiq to present for 2.5 seconds.
Alright, for the second graph, as you can see, they have a two side-by-side graph, and both graphs have multiple lines in different color. They have a red, yellow, and blue color. And then the y-axis range from 0 to 2 pu, and the red line further around 1 pu, while the green line around 0.5 pu. This suggests that the active power is constantly changing, but it generally within the normal operating range. We can see the fault time set in 2.5 seconds, and the result showed the graph in 1.113 seconds. For example, the session might allow the user choose the data and display the graph. Thank you.
Next, for this graph, show that we setting the fault time to 4.5 seconds, result in a critical time of 1.086. This important clearing time is the time required to resolve an issue in the power system so that it remains stable and function normally. This graph indicated that it became steady after 5.5 seconds and has an angle of 9.37 degree. Then, this graph shows that with the fault time set to 8.5 seconds, the critical time is 1.056. The important clearing time is the amount of time required to resolve an issue in the power system so that it remains stable and function properly. This graph revealed that it stabilized after 9.6 seconds and has an angle of 26.04 degree. Then, for the lastly, the graph demonstrates that we setting the fault time to 9.5 seconds result in a critical time of 0.934 seconds. The important clearing time is the time required to resolve an issue in the power system so that it remains stable and function normally. This graph indicated that it became steady after 10.4 seconds and has an angle of 26.78 degree. Then, for the tabulation of data, for this table show the critical clearing time is a crucial factor in maintaining system stability. It is determined by setting the fault time interval in seconds and observing the relationship between fault time and critical clearing time. As fault time increase, the critical time decrease, emphasizing in importance of rapid fault isolation. Longer fault duration result in larger phase shift across generator, impacting system stability. The most significant phase angle shift occur between fault time 4.5 and 8.5. Indicating a potential stability threshold. Then, for analysis of data, the graph showed the critical clearing time vs phase angle. The graph indicated that when the phase angle is increased, the critical clearing time is decreased. This is because to prevent the generator or rotor from breaking by ensuring the fault is cleared in the critical clearing time. If the fault is not being handled in the critical clearing time, the generator or rotor will be damaged. Thus, it is important to know how much critical clearing time is for specific phase angle.
Alright, for conclusions, the report project on phase angle analysis in power system highlight the importance of phase angle instability, especially during fault conditions. The methodology section provides a detailed description of software, symmetrical component, and flowchart used in the analysis. The critical clearing time, a constant variable in power system. Determine fault duration before system stability. Longer fault duration result in bigger phase shift impacting system stability. Thank you.